There we go. Type any questions that you have in the chat box. The video will be added to the Virtual Foundry's YouTube channel after the webinar. And I also want to tell you where we got the information. So everything that we're going to tell you about other companies that we're presenting today came from the internet. It's all stuff that you can find on the internet. The only thing that didn't come from websites is the price of the two closed systems. And I did talk with each company to get that information. So if you have more questions than what we present here, it'll be best if you talk with each company directly, and I'll give you a list of websites for all of those near the end of the webinar. First of all, that basic 3-step process that every one of these FFF metal technologies uses. And FFF is fused filament fabrication. Another term used is FDM, fused deposition modeling, and some folks also call it bound metal deposition. They're all three using the same basic 3D printing technology. They're using bound metal powder in some form. It could be a rod shape or in a filament format, and they're using that layering technique to make the shape. Then because each of these is using a bound metal powder, there is a binder included. And that binder needs to be removed. So there's a debind step included in all the processes we're going to be talking about today. And then there's the sinter step. So this step fuses those metal particles together at the edges to give you a full metal object at the end. So the first technology we're going to talk about is desktop metal studio system 2. So we're going to talk about the 4 basic steps for each of these. I just talked about 3. There is a step before all of these, and that's where you're slicing. You're getting your part ready for the actual printing process. So in the desktop metal studio system 2, for slicing, you're using Desktop Metal's proprietary software called Fabricate. And that Fabricate software controls each piece of equipment through the entire process. For printing, you're using their printer. You're using their consumables as well, which is bound metal rods, and I'll show you a picture of those in a moment. And for supports, they use a ceramic release layer.
Right. They actually print the support in the same material that you're making. So if it's 17-4 stainless, for example, the support will be 17-4, but they insert a thin layer of ceramic between the part and the supports so that it's easier to break off after the sintering process.
So you can see in that picture on the right, there's that gray metal and that white part there. That is the ceramic release layer. So post sinter, you will be able to break the support material off of your part because of that layer. So speaking of that debind and sinter step, the Studio System 2 by Desktop Metal combines the debind and sinter. So it's a thermal debind. They're doing it with just heat in their specific furnace equipment. So the furnace is going to heat the part to remove the binder, and then it will ramp up to and through the sintering temperatures. They advertise their shrink rate with their process to be about 15%. So next, moving on to the Metal X system by Markforged. For slicing, they have their proprietary software as well. It's called Eiger. And that, again, will control each piece of equipment through the entire process. For printing, you're using their printer. You're using their proprietary consumables, which are a bound powder metal filament. And the Metal X also uses a ceramic release layer. And again, the supports themselves are more of the same metal filament. It's just got that ceramic release layer in between. The parts will be sintered, debound and sintered with the supports included, that ceramic release layer allows you to break those off easily at the end of the cycle. For debinding with the Metal X, you're going to use their proprietary equipment. It's a solvent-based debinding system that uses Opteon SF79. For sintering, you'll use their proprietary equipment again. It's a tube furnace in this case, and the sinter volume on the Sinter 2 machine is 18,356 cubic centimeters. Moving from the closed systems to the open architecture filaments, we'll start with the BASF Ultrafuse. So in slicing your part for the BASF Ultrafuse, you're going to use any slicer, so the slicer of your choice. For printing, as you can see, it's a bound metal filament, and you're going to use most any FDM or FFF 3D printer. They do suggest things like a closed heated chamber and some other finer points of 3D printing, but you're using common 3D printing equipment in this case. For the supports with the BASF Ultrafuse, you're going to use that same material. Then you will either remove the supports before or after the debind and sinter process, depending on your part design. For debind and sinter, you will send your part away to a certified service bureau. There's one in the US and there's one in Europe that I know of for sure. There may be others. The Ultrafuse is using a catalytic debind process that uses vaporized nitric acid. So it's important that you're sending that away to the service providers that know how to do it. It's also sintering in a pure hydrogen environment using commercial furnace equipment. Now, there are some manufacturers working on complete systems for this process, and you can look at Raise 3D's Metal Fuse for an example. So they're working on taking this process and putting it into a closed system like the systems that we just saw, but made specially for this Ultrafuse filament so that you can work the process yourself. And the BASF shrink rates. And it is 16% in the X and Y and 20% in the Z. So not strange to learn that the Z is more than the X and Y because that orientation in the sintering furnace, gravity is going to pull that Z axis down a little bit more than the X and Y. Now moving on to the Virtual Foundry's Filamet. This is another open architecture filament. So with slicing, you're using any slicer, whatever is your favorite. As you can see, again, it's a bound metal filament form. You're using most any FDM, FFF 3D printer. And the limitation here with the most any is that you can't use a closed system like a Stratasys machine, for example. Now the Virtual Foundry has made a metal 3D printer that incorporates all the features that we like to use in-house, and that is available for our partner innovators if they choose, but you're using really the 3D printer of your choice. Supports in this case are the same material. You can use Filamet if you have only one extruder on your 3D printer, or if you have dual extrusion, you can use any support material that you would use with standard PLA, including PLA itself. And in this case, the supports will be removed before debinding and sintering.
Yeah, and I'll expand on this a little bit. On both Desktop Metal, Markforged, and BASF, the part needs to be supported in some way during the debinding and sintering process. We use a little bit different strategy. We actually bury our parts in a support, sort of like sand. We call it AL203. And that provides the support for the part. So in the BASF solution, they either recommend full supports or that you don't create an overhang at all. So we've worked around that a little bit.
Yes, thank you for that, Brad. Right on. In the other technologies, you are going through that sintering process with the supports included, most likely. With the Virtual Foundry's Filamet, and you're debinding It's a thermal debind using only heat in common kiln equipment, and you're burying your part in a refractory ballast material, and that's what's providing that part shape support. During sintering, you're sintering in that same piece of common kiln equipment in open atmosphere. You'll bury your print in a refractory ballast again and include sintering carbon for oxygen management. There are a couple of exceptions to this open atmosphere process, specifically aluminum and titanium, which both require specialized environments. So when we're talking about common kiln equipment, the aluminum and the titanium are a little bit accepted from that because they won't be able to be sintered in open atmosphere, but the majority of the Virtual Foundry's materials can be with the use of that sintering carbon.
Right. And as sort of a side note, it's under development, but we're actually working with our company that manufactures aluminum powder for us. So we're experimenting with the different additives that will simplify this process dramatically. So this may not be a caveat in the future.
We talk about a shrink rate of 7 to 20%, and I know that's a broad range. So Brad, tell us why it's that broad range like that.
Okay, so as you debind it, you're removing parts from the material. Something has to go back into the space that was previously occupied by the plastic. And what happens is it shrinks, it densifies. So you can control the shrinkage because you can control the density. So the density or the porosity that you're looking for varies by the application. So for example, we have applications in biomedical with titanium where high porosity is desirable. So the human body will actually grow bone into those pores and it becomes much, much stronger. So with our strategy, you can control both the density and the amount of shrinkage. Basically, the longer you apply heat or the more heat that you apply, the part becomes more and more dense over time. So you can control the shrinkage and the density and the porosity with your sintering cycle.
Okay, thank you for that further explanation. I've thrown a lot of information at you at once. Here it all is in a handy dandy comparison chart. So when we're looking at the 4 different technologies of FFF metal, we can see what print equipment that you'll need to use. 2 of them are proprietary machines. 2 of them are open. You're using any printer, nearly any printer you want. The debind equipment, 3 of those are using proprietary machines. 1 of them is open. You're using common equipment. Sintering as well. Sintering and debind do tend to go hand in hand. The build volumes, there are 2 specifically listed for the 2 closed systems because the printer and the sintering machines come with the system, so they do have a set build volume. With the open architecture filaments, since you're using the 3D printer of your choice, the build volume really is open and up to your 3D printer. You can see the different types of feedstock, really not any major difference in those. It's just the shape that they come in. The different slicer programs, you can see the closed systems have their own slicer programs. The open architecture filaments are open, use the slicer of your choice. You can see the different debind methods, 2 of them using heat, 1 using a solvent, 1 using a catalytic debind process. Is PPE required in order to work through this system? Desktop Metal Studio system does not require any PPP. You can do that full process start to finish without any protective equipment. The Metal X does require limited PPE for that solvent debind step. Ultrafuse says not for printing. You don't need any protective equipment for the printing process. And you're likely sending your part away. So for the debind and sinter process. So obviously you won't need any there. They'll take care of that at the place they're performing those services. Excuse me. With the Virtual Foundry's Filamet, there is no protective equipment required there either because the debind process is happening with just heat.
Right. And you're working with powdered metals in each of these situations. And sort of one of the key advantages over the bound metal strategy of metal 3D printing is that there's no air in contact with the powders. So the powders don't become airborne or anything like that. At each phase of the process, they're bound in some way.
Yes, and the only exception to that would be if you were to file your part, then you are definitely releasing metal powder. But if you're working the process, print, debind, sinter, no metal powder is released into the air. And here we have the shrink. We talked about that a little bit earlier. I did find an easy shrink number for the Studio System 2. We talked through that range of 7 to 20% for the Virtual Foundry's Filamet. The Virtual Foundry, we do have debinding and sintering instructions posted on our website, and following those instructions will yield that 7% shrink. So as Brad explained earlier, you do have control over that process, and you can hold that, or you can adjust that time and temperature profile to create more shrink, which equals more density. The second part of the comparison chart, here we're looking at the materials available from each of the processes. I won't read you the whole list. You can take a look there. That second column talks about custom materials, and is that company offering custom materials? And what I mean by that is, can I write to this company and say, hey, I want a 3D print molybdenum. Can you make me a 3D printing filament made with molybdenum? So,
And
go ahead.
I'll expand on this a little bit. So we've done materials for applications that are truly bizarre. We've done everything from moon dust simulants to piezoelectrics, which is really interesting. There's a group working on supercapacitors, 3D printing it. And so they'll have us take some unusual material and make it into a 3D printing filament. And it's becoming more common in electronics. We have a group working on thermoelectric cooling devices, purely 3D printed, things like that. So the concept of a custom material is very powerful to just the right group of users.
Yes, thank you, Brad. Those have been some of the most fun projects to work on around here when we get those custom requests. Now let's talk price. We've got the price of the system, and that means the equipment. And then we've also got the price of the materials. So let's talk through these systems, meaning equipment first. For the Desktop Metal Studio System 2, your initial investment is going to be $190,000 to $200,000. These numbers are all USD. That's going to include the printer, furnace, installation, training, software, and a starter kit of materials. So we're in a similar range here with the Metal X, $240,000 cost of entry. The Ultrafuse, since you're using the 3D printer of your choice, the cost is really going to be about what 3D printer you choose. The sintering cycles are $50 per 1 kilogram of parts. So the price range here of $2,500 to $30,000 really represents what you could potentially spend on a printer, depending on the features that you wanted to have included there. And with the Virtual Foundry's Filamet, again, the 3D printer is open, so it's the cost of your choice of 3D printer. The debind and sinter process is open as well, so it's the cost of your choice of kiln or furnace. The Virtual Foundry does also have a sintering furnace available. So if you looked at the equipment that we make available in our store, along with a starter kit to get you going with copper, for example, you're looking at an initial investment of about $6,000, but really you could spend whatever you wanted based on the 3D printer that you choose and the kiln or furnace that you choose. Now, looking at the price of materials, the list that you see here is based only on 17.4 because that's the only material that all 4 companies offer. And so the Studio System 2 is going to cost $425 for 840 cc's of media. And you can see the website there where I found that item to buy. The Metal X is going to be $162 for 200 cc's of filament. Ultrafuse charges $129 for 1 kilogram of filament through Matter Hackers. The Virtual Foundry charges $183.60 for 1 kilogram of filament, and that's through our own shop. The conclusion of the presentation really is that there are room for all technologies because everyone has a different need. The closed systems are going to provide a more plug and play option. So if you want to load your part, push a button, and get an expected part out of the end, the plug and play is going to be great for you. The open architecture filaments really offer more control over the process. The BASF Ultrafuse offers an additional step of control. The Virtual Foundry's Filamet technology offers complete control over every step of the process. So we're finding that we're helpful for people in research who really want a hands-on experience of every step of the process.
Yeah, we have a lot of customers in research. The national labs are very good customers of ours, Canadian government. Every research application you can think of, we're there. I mean, whether it's automotive, aerospace, just about anything you can think of, there are people that are sort of experimenting with it. And the key advantage of the Virtual Foundry's solution is flexibility. You have control over each of the parts. I mean, and if we make a custom material for you, you even have control of the material.
So the information that we presented today came from the websites of Desktop Metal and Markforged and BASF. Those are included there. If you're looking at the open architecture filaments and want to do a deeper dive on those, check out the website listed there. There's a compare and contrast BASF Ultrafuse and the Virtual Foundry filament on that list of research and white papers page on the virtualfoundry.com. We do have a couple of questions coming in. Can you talk about your sintering post-processing materials? So I'm going to assume that that means the sintering powders that are used in the Virtual Foundry's debind and sintering process.
Do you think they mean that, or literally post-sintering, like after we take the part out of the sintering bath? Well, I can talk about both. So in the first part of it, during the sintering process, we use a technique, we call it ballast. So we'll take the part and essentially bury it in sand. And the sand just supports any part that might overhang or distort due to gravity or the material shifting during the sintering process. And you also have to account for if there's shrinkage, it's going to cause some shifting in the material right around the part. So, and what we use is Al2O3 or a combination of Al2O3 blended with graphite, high purity graphite. In the post-processing, as they come out of the kiln, they look rough. They're not black, properly sintered. It won't be black. It'll look like the copper will look copper-ish, but the parts are made out of microparticles of metal. So it has a pretty rough surface texture that corresponds to the shape and size of the metal particles in the 3D printing filament that you start with. So typically, we just will put them in a tumbler with some type of abrasive media like silicon carbide and tumble them for an hour just to clean it up. And at that point, you don't have a mirror-like finish, but you have a nice clean part. If you want to go further, then it's just like processing any other piece of metal or jewelry or something like that with sanding and tumbling or sandblasting or whatever you pick. And this isn't unique to the Virtual Foundry. All the materials share this property.
Okay, Brad, yes, the person who asked the question mentioned magic black powder. And
Right.
Matthew, let me tell you, forget about magic black powder.
Right.
That was an early tool that we used in the debind and sintering process. That's been replaced with dry powders that are much easier to use.
Right. So yeah, right. The magic black powder, it was a it was a sort of like version 1 of what we now do with the ballast and the AL203. It was inconvenient, difficult to work with, and it's over. We've moved on.
Matthew, the new powders don't require any special storage. Will you please email me at info@thevirtualfoundry.com and let's talk about that old Magic Block powder that you have and how we can get you some better powders for you.
We'll bring you up to date.
Yeah. I haven't seen any metal performance results on the final metal, like fatigue or density, etc.
Okay. All right. Is that a question for me?
It is, yes.
Okay. We're gathering data. This is a challenging, it's not as easy to answer as you might think. People always want to compare additive manufacturing to casting or machining or something like that. And we spend a lot of our time trying to get people just to think about it a little bit differently. And as far as we do have data coming out, a group at the University of Wisconsin just published a paper on they have micro and macro hardness and some of those properties, not necessarily to fatigue and such, but we will be able to share some hardness information. We'll get that out there as quickly as we can. But the short answer is there are so many variables, and to get a perfect part, you need to sinter it very, very well. And it's easy to get a bad part. And yeah, it's challenging to quantify this particular piece of information.
Now, Ken, Brad is talking about the virtual foundry, and with all of the variables that we have, we are starting to get some data that we can publish.
Yes.
The other technologies, the other companies do have more data like this that they have published. So I'll send you to those companies for that more specific data. The next question, do you have any recommendations on where to start developing sintering profiles for custom filament?
Yeah, this is relatively easy. The debinding phase of our materials is the same. Pretty much every one of our materials, basically ramp it slowly to 900 Fahrenheit, hold it for 3 hours, and that's it. You're done with the debind. You can take the part out, handle it, or just move to the next step. So that's all the same with every material that we work with. Beyond that, the sintering properties of just about any material you can think of, you can find in a research paper. So start digging around. A good place to start is a good sintering temperature to start your analysis is 80% of the melting point. So use the profile that we've published on our website, but adapt the sintering temperature to be 80% of its melting point.
Brad, can somebody use regular AL203 as a ballast for sintering 316L filament? They're fresh out of steel blend.
Right. Yeah, this is tricky to answer. The short answer is yes, I've done it. The problem is that when we were doing this, it was very difficult to get, we had fails that I couldn't explain. When we went from just using the AL203 to using AL203 blended with graphite, which is what the steel blend is, our failure rate dramatically dropped, though we don't fully understand why. So yes, you can do it, but your chances of succeeding go down slightly.
When do you expect to do sintering testing data for the aluminum material?
Ooh, yeah, I just got a new batch in we're partnering with Filamet. They make aluminum powders, and we just got a batch with some additives in it. And so it'll likely be some type of a fluxing agent or something that can lower the melting point of the oxide layers that covers the particles in the aluminum. So there's a solution there. We'll find it. And I would say nothing goes quickly. And I was thinking 2 months. So we'll double it for Brad, and I'll say maybe 4 months, somewhere in there.
We will definitely be publishing about that when we
Yeah,
get some results to share. That will be very exciting for everyone.
yeah, this would be a really exciting breakthrough. It would make 3D printed metal parts available to just about everyone. So we're leaning into this one hard. It'll move as quickly as I can possibly move it.
Brad, can you use salt for support and to prevent oxygen from oxidizing your part during debind and sinter?
Yes. And in fact, I've actually, like table salt has a melting point. I can't remember what it is, but it's around 1400 F. And I've actually done sintering in a molten salt bath, which was a very interesting and kind of terrifying experiment. But I had success. If I had more time in the day, I would go back and spend more time working with that experiment.
Excuse me, more specifically, they said the aluminum filament can use salt.
That I wouldn't know.
Okay.
We have a user that has made a home user with simple equipment, just an off-the-shelf kiln and printer. He's made aluminum parts that have a fair amount of structural integrity. They're not bad, but that doesn't play well into the engineering demands on an aluminum part. It's not there structurally and strength wise, but we'll get it there.
When do you expect to do sintering testing on the titanium material?
Ooh, this is an exciting one. We're actually working with a couple of different sintering houses on how to bring this into sort of like the mainstream. So we have tests going. We're actually producing titanium parts that are not bad. But the application that we're working on is biomedical. So the specs are very stringent. It has to be absolute perfection. So at this point, we're getting good titanium parts, but they have too much oxygen in them and too much carbon. So as we figure out how to mitigate those two properties, yeah, it'll come into the mainstream, and hopefully by the time we're done, we'll have a sintering house that we can refer people to have them sinter their titanium parts.
And then finally, we have a little bit of a crossover question. Can you sinter the Virtual Foundry's Filamet in the same way as in the Metal X closed system, for example, with gas?
Yes.
So oxygen needs to be managed
Right.
one way or another, whether you're using that sintering carbon we talked about or gas. Those closed systems are using gas to manage oxygen. In the Virtual Foundry's open air process, we're using sintering carbon to manage that oxygen.
Right. Part of the whole strategy of the Virtual Foundry is to simplify the sintering process and make it as low tech as possible, to make it as available to as many people as possible. So the strategy we use for mitigating oxygen is carbon. So the carbon is just sacrificial. As things get warm enough, any oxygen present will react with the carbon and turn from an oxygen to carbon dioxide, which is inert to the metals. So if you can come up with a different method of getting the oxygen out of the system, that will work just as well.
And a question, how about for Australia? We definitely ship to Australia. We are working on an Australian presence. It's not ready yet, but for now you can buy directly from our store.
Yep.
You mentioned the metal powders are encapsulated during each step of the process, but are there safety concerns around handling the Al2O3? Is the particle size of concern? For example, inhalation. So this is coming from someone who's in a school, like an elementary school environment.
Right. The simple answer is dealing with any powder, there's going to be some airborne particulate. It's not difficult to mitigate. In a school, we would recommend just a simple, a vapor collection system will filter out the air. But the direct answer is, so the Al2O3 has a particle size of about 100 mesh. So it's about, I can't remember, it's quite large. So it's like 20 or 30 microns, something like that. So too large to become airborne on its own. But what happens is after you sinter a few times, you'll start to accumulate dust, and the dust does present itself as you go to remove the part from the container and that kind of thing. So not a huge deal in most applications, but in a school or something like that, I think you would want to have some type of a dust management strategy in place.
Can you use multi-metals?
Yeah.
Can you 3D print two different metals at the same time?
Yep, there's several different applications here. Like if you pick two metals with a similar melting point, you can sinter them together. And for example, like bronze and copper wouldn't be too difficult. But there's a much more interesting application, and that is where you print with, for example, copper, and the second metal print with tin. And what'll happen is during the sintering process, the tin melts and it'll infiltrate the copper. And you wind up with the bronze part in the end. This is called liquid phase sintering or transient liquid phase sintering, or sometimes it's just called embedding. Yeah, there's lots of words for it. But yeah, this is really exciting technology. And again, if we had 10 people in our lab, I think I could probably busy them all up working on some of these cool experiments. And we're hoping that users grab onto it and run with it. There's lots to explore here.
So Brad, those are all the questions from the chat from our attendees today, but I have one more very important question for you.
All right.
What do you call a chicken staring at a plate of lettuce?
I've never guessed one of these. I don't know.
It's a chicken sees a salad.
Nice.
And more information for the virtual foundry itself. We've got our discourse partner innovator forum where people go and talk about what they're working on and ask questions of each other. Reddit, YouTube, LinkedIn, Facebook. The instructions for using our materials are on our website. There's a link to the shop and the virtual foundry. You can contact us through info@thevirtualfoundry.com. So, all right, that concludes the questions and the webinar today. Thank you everyone for joining us. We appreciate it. And until next time, happy printing.
Thanks, everybody.